Alright, so in this video, we will solve the second order differential equation 2y double prime plus 3x squared y equals to 0 using a power series centered at x equals to 0. So in this case, we're going to assume a solution of the form y equals to sigma n equals 0 to infinity of c sub n x to the n. And well, because in this case, this is another second order differential equation, we will need to take all the way to the second derivative of this power series, right? So we have them here in the column to the right. So let's go ahead and substitute them into the differential equation. So this will be 2 times sigma n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 plus 3x squared sigma n equals 0 to infinity of c sub n x to the n, and let that be equal to 0. All right, so, well, let's introduce the 2 in the first series and the 3x squared in the second series. So, it'll be sigma n equals 2 to infinity of 2 n minus 1 c sub n x to the n minus 2 plus sigma n equals 0 to infinity of 3 c sub n x to the n plus 2, let that be equal to 0. All right. So the next step would be to write the series write all the series into a single one. For this, we need to make sure that both series start at the same starting index and they all have the same power of x. Well, the strategy in this case, no, in this case is to make sure the series are all written in terms of the highest power of x that we see. And well, that's not the case for the first series is written with a different power of x and also has a different starting index. All right. So since the power of the first series, which is n minus 2, and is 4 units away from the power n plus 2 in the second series, that means, well, it would be a good idea to add 4 units to go to plus 2. However, well, if I need to add this 4 in all ends in the series, well, that would mean I would need to subtract 4 in the starting index. So, however, we would be in trouble if we do this because we would be 2 steps or 2 terms into the dark side of the series. So we don't want to go there. All right. So to avoid that, um, we might want to first expand n equals 2 and 3, right? Okay, so that means I'm going to leave us with sigma n equals, oh wait, not sigma. First of all, okay, n equals to 2. So that'll be 2 times 2 times 2 minus 1, which is 1, c sub 2, x to the 2 minus 2, plus 3 times 2 times 3, rather, times 3 minus 1, which is 2, times c sub 3, x to the 3 minus 2, plus sigma n equals, now it's going to start at 4. Okay, it's going to start at 4 all the way to infinity, 3 c sub n, x to the n. Wait, that's not 3, that's supposed to be at 2. N minus 1, c sub n, x to the n minus 2, plus sigma n equals 0 to infinity of 3 c sub n, x to the n plus 2. And let that be equal to 0. All right. So at this point, well, number one, I'm going to clean up the first 2 expansions. Okay. That is 4 c2 x to the 0, which is 1 times c sub 4 c sub 2, simply 4 c sub 2. And then 2 times 3, which is 6 times 2, is that equal to 12 c sub 3 x to the first power because minus 2 equals to 1. And then let's do the complete shifting over here. So that'll be negative 4, add 4, to all n's inside of the series. So that not only will turn the first series into a series starting at 0, but also will all make it match with the power of x. So plus sigma n equals 0 to infinity of 2 times n plus 4 times n plus 3 times c sub n plus 4 x to the n plus 2 plus sigma n equals 0 to infinity of 3 c sub n x to the n plus 2 equals to 0. All right, so at this point, we're going to combine the series into a single one. All right, so this will be, okay, so 4 c sub 2 plus 12 c sub 3x plus sigma n equals 0 to infinity of 2 n plus 4 n plus 3 c sub n plus 4 plus 3 c sub n. Okay, and that's times x to the n plus 2. All right, and let that be equal to 0. So at this point, we should be good and equate coefficients. So in this case, the constant term on the left-hand side must be equal to the constant term on the right-hand side. That means for C2 equal to 0, which means C2 is going to be equal to 0. On the other hand, the coefficient of x to the first power, which in this case 12, is 12 c sub 3. That must be equal to the coefficient of x to the first power on the right, but because there's nothing, that's also equal to 0. So 12 c sub 3 x, all right, equals to 0. That is, well, not without the x, that c sub 3 equals to 0. And the coefficient of x to the n plus 2, because there's nothing on the right, that's equal to 0. That means all this expression, 2 times n plus 4, n plus 3, c sub n plus 4, plus 3, c sub n, must be all equal to 0. From here, we're going to solve for the c with the largest subscript, that is c sub n plus 4, in order to obtain our recurrence relation. That's what we're going to use to uh, get the coefficients of the solutions by series. All right, so I'm going to subtract 3 c sub n on both sides, and then I'm going to divide both sides by 2 n plus 4 n times n plus 3. So that is c sub n plus 4 equals to negative 3 c sub n divided by 2 times n plus 4 times n plus 3. All right. And well, so from here we're going to generate our coefficients. However, we're not going to generate that many coefficients. So number one thing you want to observe is that in this case, the coefficients depend on four indices earlier this time. All right, so that means the coefficients split into this time four independent chains. How are we going to describe those chains this time? Okay, check this out. C sub 0, C sub 1, C sub 2, and C sub 3. C sub 4 would go naturally back to C sub 0. All right, that's the first multiple of 4, starting at 0. All right, so that is C sub 4, C sub 8, C sub 12, etc. All right, and then for the second chain, C sub 5, C sub 9, C sub 13. For the third chain, 2 plus 4, that's C sub 6, plus 4, that's C sub 10, that plus 4, that's C sub 14, etc., etc. All right, and for C sub 3, that'll be, okay, plus 4, that's C sub, that's 7, plus 4, that's C11, and C15. All right. However, some of these chains are going to be all zeros because, in this case, because C sub 0 equals to 0, That means all the coefficients in this chain are all equal to 0. Because c sub 3 equals to 0, that means all the coefficients on this chain are all equal to 0. All right? So what are we going to have this time? Okay, so here we're going to have coefficients of the form c sub 4k, or not, 4n rather, 4n, and c sub 4n plus 1, which, well, when we get the solution by series, we're going to obtain powers of x that are multiples of 4 and powers of n that are multiples of 4 plus 1 in a similar way as in the previous example. All right. Well, let's generate some of these coefficients. So I'm going to generate coefficients for okay, so for C sub n, C sub 4n rather. So I'm going to start with 0, okay? So for n equals to 0, using the recurrence relation, which, by the way, let me box it, okay? That'll be equal to c sub 0 plus 4, that equals to 4, equals to negative 3 c sub 0 divided by 2 times 0 plus 4, which is 4, times 0 plus 3, which is 0 times 0 plus 3, which is 3. For n equals to not 1 in this case, the 4 actually, it would help if you tally this um, with a different color, okay? So we got c sub 0, c sub 4, okay, c sub 4, and then the next one will be c sub 8, all right? Well, you don't have to do this anyway. So c for c sub 4, that is going to give us c sub 8 equals to negative 3 c sub 4 over 2 times 4 plus 4, which equals to 8, times 4 plus 3, which equals to 7. But you might want to write this c sub 4 in terms of c sub 0, as we did before. 3 over 2 times 8 times 7 times c sub 4, which is negative 3 c sub 0 divided by 2 times 4 times 3. All right? That reduces to positive 3 squared c sub 0, everything divided by, what do we have here? Did you see this 2 right here? Did you see that 2 over there? Make it a 2 squared. All right, and then that's going to leave us with 8 times 7 times 4 times 3. All right. All right, so n equals to, what's that, the next multiple of 4? 8. N equals to 8. So that's going to give us the coefficient of c sub 12. All right, the coefficient c sub 12, which is the coefficient of x to the 12, just like c sub 8 is the coefficient of x to the 8, just like c sub 4 is the coefficient of x to the 4. All right, so this is equal to negative. Okay, so current relation, where are you? Okay, let me bring it down over here for us to refer to it. So that'll be negative 3 c sub 8 divided by 2 times 8 plus 4, that equals to 12, times 8 plus 3 equals to 11. However, you might want to write c sub 8 in terms of c sub 0 using the previous coefficient. So that is negative 3 c sub negative 3 over 2 times 12 times 11, all this times 3 squared c sub 0 divided by 2 squared times 8 times 7 times 4 times 3. All right. So that, let me simplify it. So that'll be negative 3 cubed, c sub 0, everything divided by 2 times 2 squared, that equals to 2 cubed. And that's 12 times 11, 8 times 7. And let me make some space. And that 4 times 3. All right. Okay, so from here, this is more than enough to write the coefficients of the first series containing the subscript of the form 4n. Consequently, the powers x to the 4n. Now let's have a look at the second chain of coefficients, that is of the form 4n plus 1. All right, so for c sub 4n plus 1, okay, so this time notice I'm not going to start at 0. I'm going to start at n equals to 1, 5, 9, etc. So for n equals to 1, okay, let's bring the recurrence relation. Again, we're going to need it to refer to it. So let's bring it down over here. So this will be uh, c sub 5 equals to negative 3 c sub 1 divided by 2. So 1 plus 4 equals to 5. 1 plus 3 equals to 4. Okay, so that's the first coefficient. Okay, the next coefficient corresponding to n equals to 5, this will be c sub uh, 5 plus 4 is that equal to 9 equals to negative 3 c sub 5 divided by 2 times, okay, 5 plus 4 is that equal to 9 and 5 plus 3 equals to 8. All right, but you might want to write the c sub 5 in terms of c sub 1. So you might replace c sub 5 with the previous coefficient, that is negative 3 over 2 times 9 times 8 times negative 3 c sub 1 divided by 2 times 5 times 4, which reduces to 3 times 3, not 9. Call it 3 squared. And negative, the negative is positive. And 2 times 2, that's also a 2 squared. 9 times 8, and 5 times 4. All right. And one more coefficient, and we should be ready to write this in segmentation. All right. So that means n equals to 9. That'll be, okay, c sub 9 plus 4 is that equal to c sub 13. That is negative 3 c sub 9 divided by 2 times 9 plus 4 is that equal to 13. Okay, times 9 plus 3 is that equal to 12. Okay, and this is equal to, because you might want to write c sub 9 in terms of c sub 1 as from before. Okay, so that is negative 3 over 2 times 13 times 12 times 3 squared c sub 1 divided by 2 squared times 9 times 8 times 5 times 4. And that equals to negative 3 cubed c sub 1 divided by 2 cubed times 13 times 12 times 9 times 8 times 5 times 4. All right. So with this, we should be ready to write all of this in sigma notation. So number one, let's write this in polynomial form. So let me start with the coefficient starting for at n equals to 0, n equals 4, etc. So in this case, we're gonna have polynomial a polynomial with powers that are multiples of 4 starting at it at c equals to 0, but c equals to 0 is the coefficient of x equals to 0, which is simply a 1. C sub 4 is the coefficient of x to the 4, c sub x equals the coefficient of x to the 8, etc. So I'm going to write y equals to c sub 0, simply x to the 0 plus c sub 4, x to the 4, plus c sub 8, x to the 8, plus c sub 12, x to the 12, etc. plus c sub 1, x to the first, plus c sub Well, the next one, c sub 5, x to the fifth, plus c sub 9, x to the 9, plus c sub 13, x to the 13, plus infinitely many terms. Okay, so I'm going to group the ones with c sub 0 and the ones with c sub 1. So I'm going to factor c sub 0, y equals to c sub 0, that times, okay, so that's a 1. And then let's just bring down the coefficient of c sub 4. So c sub 4, that is negative 3 c sub 0 over 2 times 4 times 3. Okay, so minus 3 over 2 times 4 times 3. Notice I'm not going to write c sub 0 because I'm factoring it out. That's x to the 4 plus c sub 8. What's c sub 8? C sub 8, from our calculations, that's its number 3 squared c sub 0 over all this multiplication. That is 3 squared c sub 0 over 2 squared times 8 times 7 times 4 times 3. And that's the coefficient of x to the 8th power, right? And then plus, oh, no, not plus, actually, it's minus the coefficient of x to the 12th, which is this humongous number over here. I'm just gonna bring it, okay? So that is minus 3, okay, cubed over 2 cubed times 12 times 11 times 8 times 7 times 4 times 3. That's the coefficient of x to the 12th, right? Plus infinitely many terms, of course. And then I'm going to add another line right here, c sub 1, okay? The coefficient of um, the coefficient of uh, powers that are of the form 4n plus 1. In this case, x plus c sub 5. What is c sub 5? We have it over here. Negative 3 over 2 times 5 times 4. That's actually a minus instead. Negative 2, negative 3, I mean, negative 3 over 2 times 5 times 4, x to the fifth, plus 3 squared over 2 squared times 9 times 8 times 5 times 4. All right? 2 squared times 9 times 8 times 5 times 4. All right? That's the coefficient of x to the 9th power. And then a plus that last coefficient over here. Okay, so that's a minus, not a plus. That's a minus. And that's this humongous coefficient. I'm just going to bring it 3 cubed over, what is that? 2 cubed, 13 times 12 times 9 times 8 times 5 times 4. All right, and that is x to the 13th power. And then plus infinitely many terms. Make some room so I can add all of that. All right, so all right, so with this, we should be able to write our series solution in sigma notation. Let me make even more space in between these two lines so I can add those extra factors. So the part, what stands out the most to me is the product in the denominator of of each term. For instance, 12 times 11, we're missing some factors here. 8 times 7, we're missing a couple factors here. Times 4 times 3, and we're missing a couple factors over there. Well, we sort of have this 12 factorial, but not quite. Because here we wish we had those factors over here. We can make our wish come true, of course, if we multiply by 10, okay? We multiply by 10 and by 9. Over here, we wish we had the 6 and the 5. Okay, go for it. Multiply 6 times 5 and multiply by 2 and by 1. I'm going to make a change of colors over here. I'm going to use maybe yellow here. Okay, so I'll turn this into a yellow. Well, it's important to color code this because I will write the increasing product 1 times 5 times 9, and then that times the second product 2 times 6 times 10. That's to create two increasing products. Notice how all of them differ by 4 units. In the second series, okay, in the second series, we have a similar situation. We have the 13 times 12, and then we're missing a couple of factors here. We're missing the 11 and the 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. All right, let me change color for the first factor over here. And then if I'm multiplying this in the denominator, I'm going to multiply them in the numerator as well. So that is 2 times 6 times 10, and then 3 times 7 times 11. Right. With all, we're actually pretty much ready to write our final solution. All right. So, uh, green. Okay. So for the first series, so y equals c sub 0. That'll be 1 plus sigma n equals 1 to infinity. Again, we're not going to start at 0. We're going to start it at 1 for the same reason as in the previous example. If you want to know the details, you might want to watch that video before. Okay, I want to go back to it. So this will be an alternating series. That's negative 1 to the n. What do we have? Powers of n, powers of 3 rather. So that's 3 to the n. And well, if we look at the following pattern here, okay, use different color. This is n equals 0, which is not in the series, n equals 1, n equals 2, n equals 3, etc. Over here, same, n equals 0, n equals 1, n equals 2, and n equals to 3. So notice how the powers of 2 and 3 are coincident with the number of the term that we are expanding here. However, the exponents of x, the powers of x are 4 times that n. So, and also that factorial that we see in the denominator, that's a 4n factorial. That same 4n, which is the same 4n in the exponent, that's also the factorial. So this is 3 to the n divided by, oops, 3 to the n divided by 2 to the n, and then 4n factorial. And in the numerator, what do we see? 1 times 5 times 9. Okay, so 1 times 5 times 9, dot, dot, dot. This takes us all the way to, okay, these integers differ by 4, right? By 4, n and well, in this case, for n equals to 1, 4 times 1 equals to 4. In this case, how about minus 3? That'll take me to 1. All right. Now, for the second increasing product, 2 times 6 times 10, these also differ by 4 units. Okay, let me extend the line right here. That is 2 times 6 times 10, dot, dot, dot. That is also for n, but in this case, a minus 2, because for n equals to 1, 4 times 1 equals to 4 minus 2, that's going to take us to 2. For n equals to 2, 4 times 2 equals to 8 minus 2, that equals to 6, and actually it works, right? And that's x to the 4n. Let me actually write this more in the center. That's 2 to the n, 4n factorial. Keep in mind that the parentheses matter. In a similar way for c sub 1, we're going to start with x plus sigma n equals 1 to infinity. Start with an alternating factor, okay? And I'm going to have 3 to the n, and then I'm going to do another big bar over here. All right. And then again, I'm going to have powers of 2 in the denominator. However, have a look at the factorial in the denominator. That's a 13 factorial, which coincides with the 13 power. All right. So because these powers differ by 4 units. Well, in this case, we discussed that we were generating the coefficients for c sub 4n plus 1. Okay. Those are the same powers as well. So that's going to be 4n plus 1, same 4n plus 1 factorial. And well, the increasing products, 2 times 6 times 10. So 2 times 6 times 10, dot, dot, dot. Actually, it's the same as in the one before. It's 4n minus 2. And then, what do we have? 3 times 7 times 11. And then that's 4n minus 1, right? And that actually works. So 4n minus 1. And that is the final answer for this series. Actually, this humongous series. All right.